Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tear, and today I'm going to do something a little different. This is part of a series of videos I'm going to make about infinity. I'm sure you guys are all familiar with infinity. There's a nice symbol for it, and I kind of like the symbol for infinity because it looks like an endless process. You're supposed to, I mean, it's sort of like a sideways eight, but you can imagine this kind of looks like a Mobius strip where you just keep going around and it never ends. So, kind of a nice symbol. I don't know who came up with it. But anyway, today is part one of this series. It's going to be on Hilbert's Hotel. And I guess, in case you guys aren't familiar with Hilbert's Hotel, it's a thought experiment came up with that a very famous German mathematician named Abel Hilbert came up with around the turn of the 20th century. You're supposed to imagine there's an infinite hotel, which has become known as Hilbert Hotel. So just try to imagine a hotel with infinitely many rooms. So here's the rooms. You got a guest standing in front of each room, and you're supposed to imagine that this hotel goes on forever. So it has infinitely many rooms. So here's what the paradox is. Imagine that this hotel was booked. Imagine that the host of the hotel gives everybody, there's infinitely many guests. They all want to check out the hotel. The hotel checks them all in. Everybody has their own room. Each room is numbered from one, two, three, four, five, etc., all the way to infinity, if you like. There is no number infinity, by the way, but all that means is that there's no limit to how big a number room people have. So I think we kind of understand what that means. Um, now imagine that another guest tries to check into the hotel, but there's no vacancy because all the rooms have already been occupied. They're all taken by guests. Well, you might think that there's no way to accommodate this initial additional guest because all the rooms are booked. But actually, it turns out that it's no problem. All you have to do, all the bellhop has to do is move everybody from the room they're currently in into the next room. So, for instance, the person in guest one just has to move to room two. Person in guest room has to move to room three. Person in guest three has to move to room four, so on, all the way up to infinity. And once they do that, lo and behold, there's a vacant room. Room one is now vacated because everybody else just moved up a room. This is a book, and now it's no problem accommodating the new guests. They just put them in room one. Voila. And the reason this seems like a paradox is because infinity doesn't behave the way that we expect it to. As a matter of fact, one definition of an infinite set is a set that is bijectively equivalent to a proper subset of itself. That's not possible for finite sets. If you started with a finite set, sets have what's called a cardinal number. So, say a set with five elements that has cardinal number five. That means that any other set you can do this with, make a what's called a one-to-one correspondence. That other set has to also have five elements. There's no way you can match up a set with five elements with a set with a different number of elements. But that's not true for infinity. If you have an infinite set, like Hilbert's Hotel, which has an infinite set of rooms, you can actually match it up with a proper subset. You just match up one with two, two with three, so on, and with n plus one, and then you can accommodate a new guest in room one. So now a little variation on this. Let's go back to Hilbert's Hotel. So it was no problem for us to accommodate one additional guest. But what if now infinitely many more guests want to check in at Hilbert's Hotel? So you started with infinity guests. And what if you had another infinity of guests? You might think, well, now it's clearly impossible to accommodate an infinite number of additional guests, but actually, so as I could do that as well. And here's the trick: you do another different kind of bijection, but this time, you put the original person who was in guest one into room two, and now you move the guy who was guest two in room two to room four, the guy in room three to room six, the guy in room four to room eight, so on. In general, you move the guest in room n to room 2N. So you're doubling the room numbers of every guest. Well, now look what happened when you did that. Instead of just vacating one room, you've actually vacated infinitely many rooms. You vacated all the odd number rooms. So now all we have to do is just put each new guest, each of the infinitely many new guests, into an odd number room. The first one in room 1, second one in room 3, third one in room 5, fourth one in room 7, and so on, all the way up to infinity. So not only is infinity bijectively equivalent to a proper set of a subset of itself with one additional element, it's actually bijectively equivalent to a proper set with infinitely many additional rooms. And the way people usually write this in set theory notation, a little jump in the gun, this size, it turns out there's also different sizes of infinity. I'll get to that in another video. But this infinity, this is what's called Aleph null. This is the smallest infinite cardinal number, and it's the size of the integers, if you like, or the size of the counting numbers, or positive integers, just all the numbers from 1 to infinity. That's what set theorists like to call Aleph null. And it turns out that one way people say that the previous set I showed you is bijectively equivalent that these two sets are. The thing on the bottom is Aleph null plus 1. So the way set theorists like to write that is they say Aleph null plus 1 equals Aleph null. That looks like a new form of addition. You found a cardinal number that you can add 1 to and still get what you started with. And not only that, but the cardinality, the set on the bottom here is what set theorists like to call 2 Aleph null. So 2 Aleph null is also equal to Aleph null. So anyway, that's just one of several paradoxes associated with infinity. And that's my video. That's my first video in a series about infinity. So thank you for watching, and long live math. I'll see you next time. Bye.